And this video is an introduction to gases. Just goes over some properties of gases, the property of pressure, units of pressure, a couple conversions, and then something that we call STP, which stands for standard temperature and pressure. So, all right, so way back when you learned states of matter at some, prior point in your science career, we learned that there's differences between solids, liquids, and gases, and one of those is that gases take both the shape and the volume of whatever container you put them in. And that's different from solids who do neither of those things. Solids have a definite volume and a definite shape. Liquids have a definite volume, but they take the shape of the container you put them in. Gases take both the shape and the volume of the container. So when you have gases, you have lots of particles, they're moving around, and the big deal is that collisions between those particles create pressure. Okay, and this is a huge deal. Gases, we talk about pressure with gases all of the time, and the reason we have pressure is because of the collisions between molecules. Okay, so we're going to be tying a lot of things back to the collisions happening. It's going to be a big deal for us in this chapter. Most of us know that we have an atmospheric pressure. Actually, if you ever listen to like the Weather Channel, you might hear them even say, the atmospheric pressure today is blah, blah, blah. It changes on a daily basis with the weather patterns. But atmospheric pressure is caused by gases in their atmosphere, of course. And our atmosphere, this is just like, useful knowledge. Our atmosphere, most people think it's mostly oxygen. That's false. It's actually mostly nitrogen by a whole lot. It's about 78% nitrogen. Oxygen is the number 2 gas. It's about 21% O2. And that only leaves us about 1% of some other gases that don't amount for a whole lot. Things like argon and carbon dioxide and there's some others, but those are the main ones. So we have atmospheric pressure caused by the collisions of the gases in our atmosphere. And then kind of the last thing that we'll talk about is that meteorologists use a barometer. Oh, goodness. And that measures atmospheric pressure. But there's another device that a chemist would use that would measure the pressure of a gas in a container. Okay, and so I want to draw that for you just because I want you to know that this thing exists. It's called a manometer. It's kind of a strange name, but it measures the pressure of a gas in an enclosed container. So a manometer kind of looks like this. Give me a second to draw it. So you have this like flask of some sort that's then connected to like a tube. My drawing's not very good. Okay, and what's in this tube is mercury. Okay, so when the cylinder here, or the vessel is empty, the levels of mercury are even, okay, across the apparatus. But then what happens is they put a gas in here, okay, and those gas particles collide with each other and they create a pressure. And so what happens is that pushes the mercury level, I should have drawn it more like this, like the mercury level is even without the gas. And then when you put that gas in there, oh darn, let me redraw that. Okay, so when you put the gas in and it floats into here and pushes the mercury down, which raises it on this side. Okay, so now your mercury is offset and it looks like this. And then how they measure a pressure is they actually measure the distance that mercury moved, and they measure it in millimeters. And the one unit for pressure that we're going to learn in just a second is the unit of millimeters of mercury, and that's where it comes from, because it seems like a really weird unit, but it comes from this device that's called a manometer that allows a chemist to measure the pressure of a gas in a sample. Okay, so what are some units for pressure? The most common unit for pressure is called the atmosphere, and it gets the abbreviation ATM. Okay, and so 1 atmosphere, okay, that's actually the pressure at sea level. And I hope you know that sea level means, the level that the oceans are. So like here where we live, we're absolutely above sea level. So our pressure is a little bit different. We'll talk about that later. But 1 atmosphere is the pressure at sea level. Okay, so there are some other units for pressure, one of them being millimeters of mercury that we just discussed. And so what I'm going to do here is not only talk about the units, but also talk about the conversion factors. So 1 atmosphere, or 1 ATM, is actually equal to 760 millimeters of mercury. So that's a conversion factor. There's a second unit or a third unit, I guess, of pressure called the torr. And 1 atmosphere is actually equal to 760 torr. So knowing that, the torr and the millimeter of mercury are equal, right? 760 equals 760. So these are just conversion factors. There's another unit called the Pascal. It's actually named after a person. That's a person's last name. So 1 atmosphere equals 101.3, but pascals are really small, so we often use the abbreviation kilo. Okay, pascals, obviously kilo, like kilogram. But if we wanted to do pascals, again, they're really small. 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. And then maybe the unit of pressure that you're familiar with, if you're familiar with any, would be pounds per square inch, or PSI. And you might know that if you might not know that at all, but you might know it if you've ever worked with putting air in your tires, right? Your tires have to be at a certain pressure, and most of the time that's reported as 32 PSI, okay, pounds per square inch. But these are just all conversion factors, and it's important for us to be able to convert between units of pressure, not necessarily to have them memorized, okay? So the next part is just 2 little practice conversion problems. So if I were you, I'd pause this video, use these conversions and attempt to convert these. I'm sure that you'll be successful, and then I will just go ahead and solve them. All right, so convert 1.75 atmospheres to millimeters of mercury. Oops. That would be atmospheres. Okay, so I set up my conversion factor. I want to go from atmospheres to millimeters of mercury, and that's that first conversion right here. So 1 ATM, 760 millimeters of mercury, and I multiply. And I'm going to stick with 3 sig figs because that was what I was given in my problem. So to 3 sig figs, that is 1,330 millimeters of mercury. So pretty simple conversion. And then convert 72.7 atmospheres to pascals. So, oops. Excuse me. So up here, I know that 1 atmosphere is equal to this many pascals. So 1 atmosphere, 1.013 times 10 to the 5th. It's going to be a big number, obviously. And again, I'm going to stick with 3 sig figs because they gave me 3 here. So to 3 sig figs, this comes out as 7.36 times 10 to the 6th. pascals. So again, you should be able to use these conversions to perform, or use these conversion factors to perform conversions with pressure units. All right, and the last kind of topic for this intro is something called STP, or standard temperature and pressure. And basically, it's just a set of conditions, and scientists and chemists use them to kind of standardize the discussion of gases. This is definitely, of course, pressure deals with gases. So when we talk about STP, we're always normally referring to gases. And so this is just a set of conditions that it's a temperature and a pressure. It's all it is. So the standard temperature is set at 0 degrees Celsius, and the pressure is 1 atmosphere. So those are the standard temperature and pressure conditions, I guess. And so you're actually given some information. Like if somebody were to say to you, the reaction occurred at STP. Okay, well, when you hear that, you don't really think you're given much information, but you're actually given the fact that the reaction occurred at 0 degrees Celsius, and it occurred at a pressure of 1 atmosphere. Okay, so there's actually some data embedded in that, in just saying that something occurs at STP. This is going to be a big deal for us in this chapter. And there's one more thing we can do, which is relate STP to mole calculations. And so, there's a conversion factor that says at STP, 1 mole of a gas occupies a volume of 22.4 liters. Okay, so that becomes a conversion factor for gases only at STP. Okay, so like if you were told, let me see if I can make this make sense. If you were told that you have 1 mole of oxygen at STP, okay, then you know that volume is 22.4 liters. Or if you had, 1.6 moles, you could just use that as a conversion factor. However, if you're told that you have 1 mole, of nitrogen, but you're not told it's at STP, or maybe you're told it's at like a temperature of 25 degrees Celsius, for instance, then with our knowledge right now, we don't know the volume. Okay, and that's because this mole to volume relationship is only true, this one that we've just discussed, is only true at STP. Okay, and that's a big deal. This is often referred to as the molar volume of a gas. And again, this is a conversion factor, but it's a conversion factor with the stipulation that gas is at conditions of STP. Okay, so that's kind of the intro to gases. So, some properties